So welcome to part 2 of building a Apollo guidance control computer. So remember in part 1 we built this little breadboard thing with our 2 NOR gate chips just to show you how they worked. Here's one of the designs someone did up on a CAD program. I printed out really nice and big. And take a note at a couple of these local ones. They have each chip labeled at the bottom, and each gate has its own number at the top. So this is your gate number, this is your chip number, and from that you can, and then they name the pins for the chips A, B, C, up through K. Instead of using numbers like we do now, I assume it's just because of back then. Because they only have 2 per chip and I have 3, I can't use their numbering. So what I did is on pencil, like this is U4, it means it's chip 4, and I numbered the pins in pencil. And so I did that for this whole big thing. Ended up writing them up on a piece of paper like this. Typed them up in Excel, printed them out nice and neat. And then double checked them twice to make sure that they're okay and they all match up. And so now we get to design a printed circuit board for this whole thing. This is just one of the modules, or one half of the module. The other half of the module is the second sheet, and it's almost the same thing. If you remember, the circuit we made last time was that circuit there, and you'll notice it's very similar and it repeats over and over and over and over and over and over and over. So it's just the same circuit multiple times so they can slow down the pulse each time. Because remember, this pulse comes in and it goes out at half the speed. So here it'll be quarter, eighth, 16th, or 16th the speed, and so on and so on. And I'm not sure why they needed to do this bottom row, that top row, and then both back sides, but I'm sure it makes sense later on. So I got my knowledge of printed circuit boards from my dad when I was a kid, and he was an electrical engineer basically in the 70s. So what it consisted of is you had these, it's basically a fiberglass base with copper on top. And what you do is you take a Sharpie, you draw out your circuit on top of this, and then once you get it drawn out, you dip it in ferric chloride, and this ferric chloride will eat away copper that's not covered up. So this isn't Sharpie, but you can do whatever design you want, and then whatever's covered won't be eaten up, but whatever is uncovered will be eaten up. So here's what I did for a project, and I just drew out the little things, run the components through, solder them on, and that's how your circuit board works. But there's all kinds of different sizes. What is this one? So the printed circuit boards for the Apollo mission were 9 inches wide. This is a little bit bigger. Each one of these is going to be one of these chips on there. And you would just get a board wide enough, draw out your lines on it, dip it in ferric chloride, and since they were multi-layer, you're going to have different circuit diagrams for each layer and stack them on top of each other. And they use, currently they use something called pre-preg, which is basically a fiberglass sheet. They lay it on, stick it on, lay another one on, stick it on, put it in a press, heat it up, and the heat and the pressure causes the epoxy to cure. And then I guess they'd have to drill pins all the way through each of these, through all the layers, and each one of these all the way through. And that's how you would do it. So when you're designing a multi-layer circuit board, I have no idea how to do it. I asked my dad how it was done. He had never even heard of it being done. So what I came up with is using acetate. So I made these little stands there. That one's loose. Put the acetate on. And we used our diagram, our big diagram, and all my pinouts. So before we start, there's a number of pins that they have listed as spare pins that aren't used. So let's go ahead and try and cross those out so we don't accidentally use them. Remember our diagram from before. Turn it sideways. Ground is pin 7. So when we have our chip like this, sideways, that one's ground, that one's positive, and we got to run ground to each of those. And the way I do the multi-layer is this will be one layer, next piece of acetate to the next layer, and I can take on and off the layers as needed. So I'll probably speed some of this up. I probably won't even video all of this, but I'm going to try and do all the layers. The Apollo ones use 7 layers. I don't know if I can get one mass produced that is 7 layers, but we'll see what we can do. And if I can get a whole bunch of them made, I'm going to see if I can sell them to anybody else who wants to try this at home themselves. And you won't have to go through this whole nonsense. And also, if you come up with a better way of doing it, you can just, like I showed you, wipe it off and start over. Now I've done this correctly and carefully. There's my mask. Take a sheet like this, cover it in the photosensitive chemicals, put it on top, flash it with ultraviolet light so the chemicals get destroyed that are hit by the light. Wipe it off, we'll leave that mask, cover it in ferric chloride, dunk it in there for a few hours, pull it out, and it would look just like this, but with my pattern. Go ahead and do the voltage positive one. Okay, so here it is a couple days later, and I was going to do all the chips, but it was tedious and I'm not going to be able to really use it with how I was going about it. But here's the ground layer which would be somewhat similar to that. The voltage layer connecting to the pins. The first of the circuit layers. You see how I went all the way across. And the other ones I just did the first 2 chips. And then this layer. See, it gets to be a bit of a mess over there. Like I said, what I thought they would originally do is once I get one of these done, let's use the ground one because that's some black and that's easy to use. They'd cover this in a chemical that was light sensitive, put a mask on, ultraviolet light over it, and once the ultraviolet reacted to all the stuff that wasn't masked, you take it out of the ultraviolet light, you wipe off those chemicals, and then you had the mask on the copper, you dip it in ferric chloride, and then the ferric chloride would eat all the copper, it's only on the one side, that wasn't masked. And so you have a copper cutout similar to this, which is basically exactly how this looks. This was made, I used a Sharpie when I did that. But I came to the realization there are 7-layer circuit boards, and the drawing specification said it had to be less than 1/4 inch thick. So let's pull out this ruler. See how thick these are. Okay, I don't know if you can see that, but that's a 1/16 of an inch. So that means 4 of these. Right there. It's about 1/4 of an inch. My thumb's in the way. So right there, it's about 1/4 of an inch. Now, in addition to just the circuit boards, they'd put a layer of pre-preg, which is basically a layer of fiberglass. So these 4 would actually be over 1/4 inch, and then with 7 layers is what they used. So that'd be nearly 1/2 inch thick. And the specifications on the drawings is 1/4 inch. So that made me realize that they weren't actually using these boards. What they could have been doing is a thinner board maybe. But I took apart my Mustang, 69 Mustang, and it had an interesting circuit board. That was basically Mylar, which isn't much different than this acetate sheet. So they would print the circuit on a sheet of acetate, I believe, and they would just glue the sheets on top of each other. Just like when I lined them up on here. You'd get it on some kind of a jig to hold it perfectly in place, probably with pins, something better than this. Put a layer of glue on, glue the next layer on, layer of glue, next layer, and on and on and on. And each layer had to have the holes in there. Actually, you probably had to put the holes in after because the glue would fill them up. And then right here, I have 5 layers. And it's perfectly thin. And after you get your 5 layers glued on top of each other, Mylar, you glue it back here like this, like an old duty circuit board, to give it rigidity, so you can put the chips on there. So the second issue I realized afterwards is I'm used to working with chips packaged for breadboards. You guys remember this from my first video. The pins are perfectly spaced to fit on the holes of a breadboard. They used what was called a surface mount.
which I didn't even think about was going to be smaller. But you see the size difference? So I was thinking I could hand draw stuff because of how big these pins are, but look how big those pins are. These two chips are exact same chip. This is just designed for surface mount. What you see fits pretty close to my drawing. I enlarged the drawing to make it a little bit easier. It's supposed to be about this wide. I enlarged it to that size. Give myself a little more room. So you see there's very little room for error. Put on millimeters when dealing with it. With these ones you can pretty much hand draw. So what I'm going to end up doing, which they couldn't have done back in the day, is I'm going to use a circuit board CAD program to make these masks, the circuit board layouts. And then I got lots of ways I can do it. I can either, I've seen hand pins similar to this, similar to these, that will write with electrical conductive ink. And I could hand draw it following putting a piece of Mylar over my template that's printed out from the computer. So I'd have my template, and I would just basically copy the template out however it has to go with that conductive ink. Second way is I can get sheets like this that will print out on an inkjet, and I can try and get a inkjet cartridge with that electrical ink, which I believe I've seen before. So I put blank sheets. It could probably even be acetate. Just grab a blank sheet, stick it in my printer, print it out, print the circuit design. It'll come out like this, but with conductive ink. And if I print them out all on top of each other, glue the sheets up, put the holes in. And for the holes, they pretty much have to be exact. And since I'm making a whole bunch of these, because there's going to be over 50 of them, I think 52, that I was going to make a wooden jig with pins just sticking out, just barely, put these sheets on top and roll over it with a rubber roller to poke holes in it. And then you had to put some kind of pin or solder down the holes, and then we'll see if that electrical connection works. And that should do it for us. But the intent of this video was to show you how they would have ended up doing it. And they'd end up doing it by hand like this to create the mask. And then they have a Mylar sheet similar to this, cut over, drop it in ferric chloride, and they'd end up with Mylar sheets and back it with something like that. That would be just fiberglass board. And then they'd stick all these chips on and solder them in place. And the good news about these chips is I was able to find chips that work between 2 volts and 8 volts. And typically modern circuits are all 5 volts. The Apollo was 4 volts. These will work down to 2 volts. So that means it'll work perfectly fine on 4 volts. So I'll be able to use the Apollo power supply, whatever it was, and they should work just fine. The only difference is these are transistor logic, and they used resistor logic, which basically work the same. Theirs just were slower. So that's it for this one. I'm going to do some experimenting and see what I can come up with, printing it out on Mylar or acetate. We'll see how well that works out. Alright, see you next video.